And then that moves to almost the last section, which is how to achieve high performance. Or in this case, look that this user was doing 2x2 MIMO. With these rates, I would say that is 100 megahertz even. And with 100 2x2, he sees a very high blur. So we are reaching a point that you need to start looking at what we were saying before of the threading, the real-time failures, and why is that happening. Typically, above 50 megahertz 2x2, you need to start worrying about these things. If you're running lower than that, it shouldn't be a problem unless something is very wrong in the setup. If you want to go high performance, what I would recommend is always start with a wired setup or a shield box, because even if it's on a srsRAN and you own the spectrum, you can have issues. For instance, when doing MIMO, if the antennas are like this, the MIMO channel is very bad, or I don't know. There can be scatters that are constructing in a destructive manner. Always, I would recommend to start with a shield box and with a wired setup. Very important, make sure that you didn't compile with debug. Sometimes people is experimenting and wants to run the debugger to go step by step, and then forgets to, when they want to achieve performance, forgets that the code is compiled in debug mode. By default, we always choose release. So unless you mess with it, it shouldn't be a problem. Set lock level to warning and disable pickup. The pickup especially is a killer the Mac pickup, especially if you want to achieve performance, because it writes to the disk. So always disable. The logs, although we put a lot of effort on making them very efficient, depending on, it can be very spammy. Depending on the log level that you set, it can be generating a lot of strings, and that will also kill the performance. Make sure that the CPUs are set to performance, and remember that's with that script that we provide. Make sure that you don't have other tasks running in the background. Always, I recommend trying first with UDP, not TCP. TCP is very tricky, and everything has to be very well configured if you want to achieve maximum rate in TCP. Always start with UDP. Always start first with downlink only. When that works, do uplink only. When that works, do bidirectional. But try to start with the simplest case. Reducing K1 and K2 usually helps a lot. You can do that in the configuration file. This is how, when you run, this is what you want to see. This is the ideal setup. Here, this is a test that we did with Viavi in a Dell server in our lab. And what you see here is that there are 0 KOs, both in uplink and both in uplink and both in downlink. In this case, even I wasn't pushing to the maximum, so the maximum is 1.4, and this is why the buffer state is not top. But when you have a shield box or a wired setup, you should be able to run for 1 minute, 10 minutes, and don't see any retransmission. This is a well-calibrated system. If you're in a wired setup and you see retransmissions, most likely are caused by lates. And as I said at the beginning, maybe in most of your work, this is not critical, and it's fine if you are doing an experiment 10 minutes and there are a few retransmissions, nobody cares. But if you are aiming, or when we aim at a commercial grade deployment, you look at not only 10 minutes, but you look at many hours with a single retransmission. And when you run HTOP is your friend when you are trying to optimize your system. There is an option that tells you the names of the threads, and then you can see how things are working and if there is something that you need to do. In this case, for instance, we are running in a 12-core, 24-thread Xeon Gold, and it's well tuned because all the threads, there is no thread that is very loaded. If you remember the histogram that I was showing before, always there are some outliers in the execution time of a task because things can align very badly due to memory collisions, due to interrupts with the hardware. Many things can happen in the machine that suddenly one task takes more time to execute. There are many things that can be done in a platform to really tune it for performance and reduce this. And so that this histogram is more confined. But still, it can happen. So always it is recommended that you add some margin to your workload. So if you have a task that, let's say that here in this case, the deadline, so we would need a CPU such that this task completes, I don't know, 80% of the times or 90% of the times in half of the deadline. That means that translates in all the threads being ideally less than 50% loaded. If you see, we explained before what these threads were. For instance, the PDSCH threads are the ones that encode the code blocks in the downlink. So there are, in this execution, there are 7 threads doing this task. So if you see that the workload is very low, maybe you can reduce this value and don't use so many resources. If you see that the load is very high, you should increase this value. How do you see the lates in the, so let's say that, okay, I'm seeing some blur here. I see some blur here. What do? I have already set the log level to warning. And then what I should see is that with the log level set to warning, I shouldn't see any message in the log. If I see messages in the log, most likely are by these real-time false. At the moment, it's true that the messages that we generate are not very clear on where the problem is, but typically you would see when things fail these 4 categories of messages. This one that let me see if I have that slide. Yeah, if you remember this previous slide that we classified the lates from L2, Phi, OFH, and HARQ. These are the messages that you will see associated to this classification. This message says that the L2 was late in generating the downlink TTI and TX data message. This message here, for instance, says that the Phi was late in delivering the resource grid. This message says that it's generated by the OFH and says that there are Ethernet frames that are late in the transmitter queue, so it's not transmitting fast enough. This message says that the HARQ indication arrived late at the scheduler, so it can't reuse that process. So these messages here tell you which of these cases you are seeing, and hopefully can help you to fine-tune the system and optimize it. These are a few things that can be done to optimize the system or to improve. So the reason for a late happening, let's say for one of these outliers to happen, can be different, can be actually many. Not always it's a problem that the computation is slow. It can be that the operating system, for instance, is interrupting a thread, or that the operating system is being late and waking up a thread. So for instance, when the operating system is late in wake up threads, what we recommend is to use a real-time kernel. If there are interrupts from device drivers or like Ethernet into the operating system, our recommendation is to use CPU isolation. This is something that you do in the group, for instance. This, as I said, in many cases, maybe you don't need to do that because you are fine with just 40 megahertz or 20 megahertz and you don't need to do full rate. But if you really need to achieve the top rates and do not see any late, you will need to do this. If the network especially the front haul is slow, you will need to start using DPDK. DPDK is an optional dependency. You don't need it when you run. But if you want to achieve high performance, you will need to compile with it. If you see lates in the doubling, so this, remember, you would see a message like this. One thing that you can do is increase the number of PDSCH threads. It's a configuration option that we'll see now, or increase the pipeline length. But if you increase the pipeline length, you will also have more latency. If you are doing research in low latency, maybe you don't want this. And if you have too many HRQ-lates, actually you should reduce the pipeline length, because that means that the scheduler needs the feedback very in advance and is not being delivered on time. So everything is a trade-off and an equilibrium. And at least the good thing is that we give you the flexibility to configure all this. So by default, we provide threading options and let's say the number of threads and the size of the pipeline for this typical configuration. So a big server with more than 16 cores, some intermediate machine between 8 and 16 cores, and between 4 and 8, and between 1 and 3. We provide like profiles or default configurations. If you want to customize, you want to look at these two sections. One is the expert file section that allows you to configure the pipeline length, or max proc delay, we call. And then the expert execution section have two sections. One for affinities, which is what we were discussing before, where you can define the CPU affinity of, for instance, the L1 downlink and uplink threads, the L2 cell thread, also the low priority threads, and the threads of the RU. You can decide different mapping, for instance. But as I said before, by default, this is left to all the CPUs available, and it's what we have found that works best, but maybe we're wrong. In this section, you can configure all these parameters that we have seen before. Remember the number of threads in PDSCH. For instance, you would configure here the number of threads for the PDSCH. This is the number of downlink and uplink threads that, if you remember the pipeline diagram, where are the ones that run on every stage of the pipeline. So as we said before, how to improve? If I see that the PDSCH threads are too high, the CPU load, I can increase the number of PDSCH threads. If I see that the PDSCH threads here are too high, I can increase the number of PDSCH threads. This is the last section. So before I finish on this threading, any question? Yeah.
Ismail, for the performance that you did at 1.4 gigabit, was that fully software or was that acceleration?
That only software. That performance is actually is this capture. In this capture, I'm doing 1.4 gigabits. And this is the total occupancy. So it's almost 7 cores. but it's only software.
And if you had to add acceleration, would you think you get a higher rate or lower latency or both?
So if you have acceleration, you can do all this. You can do lower latency, so you can reduce. Let me go back to the diagram. So with hardware acceleration, since these tasks take much less to complete, you can reduce the pipeline length. That reduces latency, and and you can use you can essentially also process more per slot, so you can also increase the throughput, but the throughput will be limited by the cell throughput. What our initial experiments tell us is that roughly we can multiply by 3 the throughput or reduce by 3 the overhead. So in the same server, we haven't yet experimented it, but in a server like the Xeon Gold that we use, let's say that without acceleration you can run 2 cells. With acceleration, we think that you can run 6.
Okay.
Just follow up on this question. Just wonder if you have any references or pointers somewhere that kind of systematically characterize the resources needed for different kind of configurations like UEs, traffic load, and so on. That we use as a reference.
So the number of UEs will not affect a lot. So the resources used here is for when the GNOD is using the entire resources of the cell. It's only it's allocating everything to a single user. But if you have 10 users, every user will have 1/10 of the rate. And so the PDSCH workload, for instance, will be the same in total. The only thing that increases when you have multiple users is the DU cell. The DU cell, remember, is the thread that is computing the scheduler and the FAPI messages that go on every slot. And since there are more FAPI messages every slot, it takes a little bit more to compute. Yeah.
Thank you.
Okay, so the last section is if you even want to go even further in your debugging of the system or in understanding, in this particular case, the physical layer, we recommend to visit this repository. This is a set of tools that we released. It's also open source that we have used and will still use to test our own PHY and to develop our own PHY. It does different things. For instance, it generates test vectors that we used in our unit test to verify that the signal that we generate is according to the spec. By the way, it uses the 5G toolbox, so you might have some license restriction. It also has the capability to generate a MEX file from our C++ blocks and compare it with the MATLAB implementation. And we use this to generate end-to-end simulations. And probably most important for if you are debugging or using the GNOD is that it also provides tools to analyze IQ dumps. So how to do it? In the log section, you will see that there is an option to set the PHY RX symbols file name. This, what we'll do, if you enable this and set a path to it, what it will do is that every uplink transmission will store the entire resource grid in a file. You have to set also the file level to debug. And then what you see in the logs is that for every time slot, like this one, you will see another line that says the RX symbol has been saved And this is the offset for this slot. Just don't care about this for now. And this is the number of bytes that were written. In this log line, for the PUSCH, since you have set it in debug, you have many more information than before. Then if you go to MATLAB, you go into this folder in the repository, type this command, and then you just go to your log, copy the entire section that corresponds to the PUSCH reception, go back to MATLAB, type Y here to continue. You just need to enter the subcarrier spacing and the grid size, and then you run. So then at that point, the signal and the configuration of the signal has been stored in the MATLAB environment. Then you can run SRS PSH analyzer, and you pass these values that we saw before in the logs and the path to the data capture, and it generates plots like this. Then you have all this in your environment in MATLAB, and then can play with it, look at the signals. Here you will see the samples in the resource grid as we receive them, but also it gives you the samples at every stage of the signal processing. So this is after we did channel estimation and the magnitude and the phase, and this is the plot of the constellation as we are seeing when we decode it. And this is also useful to debug, for instance, synchronization issues or things like that. And that's all I have. Yeah, more questions. Yeah, no, we don't have that yet. No. Yeah. No, at the moment we don't have a real-time constellation plot. You can use this to capture a file and then post-process it. So what did you say? Is working? Okay, so yeah, now Andre will show what this demo, he has been showing it all these 2 days, but now we will show it again.
Okay. Yes, let's start. I guess you have been wondering why we have been passing through and then checking all that. That's because we actually try our best to kind of lower the complexity of ORAN a little bit by providing, good software, and then trying to also downsize all of that a little bit. But obviously we can't get rid of all the complexity. And one of the biggest complexities is actually the synchronization. So which involves PTP, so the time precision protocol, and it requires GPS satellites to log and a device there that synchronizes the RU and the DU. And every so often it just failed. So we acquired a log there, we acquired a log here, but then it got rid of the log. In the meanwhile, I've been preparing like a backup demo using a B200, but fortunately we don't have to use that anymore. So we can do the real demo, let's say. I guess some of you have seen the demo setup that also Ismail briefly presented in the slides. So it's essentially, the demo essentially tries to serve 2 purposes. One is, yes, showing that we have actually integrated with a third-party ORAN RU using our G0B and the open fronthaul implementation to talk to the RU. And that's, in this case, the Foxconn RU, which we run in a 100 megahertz channel in a 2x2 MIMO configuration. And the second purpose is, as I already said, kind of trying to lower the barrier for O-RAN. So instead of having to carry, big servers around and, heavy and expensive equipment, we kind of wanted to fit it all into a relatively small transportable size. And that's why we kind of used this kind of bare bone system that is enough to run the cell with that configuration, that it all fits into one suitcase and can be carried around. So all the entire table minus the monitors can be carried around, and that's what we are showing here. And then, yeah, let me briefly talk you through that through the steps. So we have one third component that we have here also on the screen is it's actually a Raspberry Pi that is using the console output of the G0B as one way to display all the statistics of the Mac layer. So the UEs that are connected, the rates that they are achieving, buffer status reports, MCS indices that have been assigned. Another way is to actually save a JSON file in the same granularity. So you get per every second, you get all those statistics also in a JSON file. And we, just before the workshop, actually, we had a Grafana-based visualization tool, which basically takes this JSON and shows it in a visually appealing way. So that's what you can see here. And a third component I have here is actually a spectrum analyzer using a Blade RF connected to my computer that we can now use to show the spectrum. So let me. It's my thing. Back. Is it back? Cool. Okay. So what you're seeing here in the background is actually already the G0B running. I have another console here that runs the core network that has been prepared before. It's actually also co-located with the G0B on that box here. So that's a standard Open5GIS that we run in the background that has the credentials for the phones in its database and that allows us to attach those phones. And then this is the console showing geophosphor, so the spectrum analyzer that we are going to use. I'm just stopping that and starting that again. So it's actually using this Blade RF. It's actually a little bit slower because we're streaming that over the Meet. Anymore? Yeah. Yeah, why not? Yeah. So I can actually also leave the Hangouts now, no? Yes. Display mirror. Changes. That should be it, no? Can you see that? Yeah. Cool. So that's now a little bit faster. Cool. So let me go back to the console and switch back to the G0B that's actually running in the background. So we already have a UE attached here as well. That is actually this phone. So I'm gonna take that array. So we'll detach. So there's nothing running now because there's no G0B on, no UE attached. So now I stop that. We look at the spectrum analyzer. Basically, we have this empty spectrum. And what I'm using here is like the typical command. So using the application that we've explained, G0B, and then we have prepared a workshop demo YAML configuration. It contains all the various configuration parameters that we are using. So let me just quickly start that here. And also, so that's running now, and also verified in the spectrum. So you can see the GNOB actually broadcasting the system information block and the SSB, but there's no user attached. So no, that's just the typical broadcast traffic that's going on there on the cell. And now let's have a brief look at the workshop demo and what parameters we're using here. Just obviously you will see those, and that they by now should look familiar. So it's the AMF configuration that's pointing to a local host address. So because this the Open5GS instance is actually running on the same computer. And then the first section is the RU configuration section, including all those timing window parameters, the compression. Those are all those values that Ismail explained that need to match with the RU. The scaling, the Ethernet configurations of the MAC addresses. In this case, we're using DPDK, so that's an optimization to bypass the networking kernel of Linux. So it's all passed directly to the user space. In this case, we're not using the network interface here, but it's still useful to use the same configuration there in case you don't use DPDK. This is the main DPDK configuration, so this hardware abstraction layer, because we have also other accelerator configurations, and in the future maybe also others. So that's kind of abstracted away here. The CUCP configuration, then the cell configuration that actually defines the downlink AFCAN. That's also obviously needs to match with the frequency that the RU is configured in, and in our case also the FCC license that we have here for that demo using the CBRS band is exactly this. And then the bandwidth, the cell bandwidth, in this case 100 megahertz, the carrier spacing, the PCI tag, the downlink configuration, or the antenna configuration, sorry, in this case I said 2x2 MIMO, so it's 2 downlink antennas and 1 uplink antenna, the bridge configuration, and then various parameters for the various channels. So the SSB periodicity, so how often this is sent, and the downlink, the PSSEH, including schedule and request periodicity. So how often can a UE actually request resources to the GNOB to get eventually uplink allocation, things like that. And that's a configuration that we kind of fine-tuned a little bit for the setup here, but it's there's nothing like special about it. So I'm happy to share that as well, along with the setup guide and all that. Then in the SSB block power that also has been mentioned, the uplink configuration, the slot configuration, so the uplink downlink pattern, and then logs. And this configuration, so this is the default value, so to just log warning, like for all layers, log them in warning, and then commented out a few, interesting levels. That by far there are a few more log levels that can be enabled as they should be required, and a PCAP as well. Again, so MAC PCAPs are disabled, NGApp, even though they are a lot less spammy, let's say, we have chosen to disable them in that configuration. And this expert execution, like the threading, allocation of the PDSEH threads, downlink threads, and the processing delay. And then there's another configuration, which is usually in an exa YAML file called quas YAML, which defines for all the 5 QIs, so all the different 5 QIs essentially that the core network can actually request to set up a bearer for, a bearer. And then this includes for each 5 QI, the RRC configuration as well as the PDCP configuration. So those are given internally to the CUUP for the PDCP and to the DU for the RRC configuration. And then again, all the parameters can be modified, the retransmission of the status requests and all those parameters, sequence number lengths, stuff like this. And at the end, it's this metric section that tells the GNLB to also write to that GNLB metrics, the JSON file, period in a periodic manner, the MAC output that is also displayed by default on the screen. And that's really it. And then we've all condensed in one config file. I personally, or like we usually choose to put the various section in different files and combine them as we see fit. Like this combination feature that Ismail mentioned, it's very handy. So you could, for instance, have one configuration that picks a core running locally, one in Docker, one maybe in the lab or so, and then you can just mix and match them, which is really cool. And coming back to this one, so it's still GNLB is running. We can see that here, and going back to the console here, enabling the trace, and now it's time to actually use a handset and try to attach. So that's just a normal Motorola handset here. That I will now take out of airplane mode and see it hopefully attaching, and that's how it should look like though. So the phone immediately attached to that cell, and we see that it's not doing much, but it's attaching here, and then we see every second we see some statistics. And the same, I think you should also be seeing here on the dashboard, it's the same dashboard that we see here. So that the phone has attached, and but it's not doing much. And then actually it's interesting to like do the same experiment, but watching not at the console, but at the spectrum analyzer. So I'm taking it out of airplane mode again. So it's again just the SSBs being transmitted. And when I turn off airplane mode, you see it ratcheting and doing the initial handshake, which actually looks quite cool as well to see that. And then it's basically going on with those periodic messages. So the next thing we can do is obviously doing a speed test. And that's actually also quite cool because you can see how it's ramping up and how as the throughput increases and kind of reaches its maximum, how the scheduler allocates more and more resources to the UE and then see the spectrum actually being occupied more and more. Still, I mean, you'll see gaps because it's a TDD, traffic configuration. It's a downlink heavy application, but it's quite cool. So I'm just hitting that here. That's Ookla speed test. So now it's kind of picking a server, and then now it's going, and it's more and more. So 580 megabits per second. And by now you should be seeing that also here on the screen. And then the speed is over. Can do the same again. Again, see it like filling up the spectrum. This time doing 550 megabits per second. And then another application that is actually also interesting to see is I always choose actually YouTube video because you can also observe the buffering strategy that YouTube uses. So this is a streaming in a 4K video. You see kind of those peaks that YouTube uses to buffer data, and then the playback. Go and streaming in again. So you have those quick bursts there, doing like of the YouTube client to buffer the data. And again, the same is the same output you can see here on the console. Another experiment that we can do to actually get to the peak rate of the cell, which is sometimes not achieved with with the internet connection, because we are using the backhaul here of the CCI network, and even though it's a high bandwidth connection, it's still 1 gigabit. Even with the computer, I'm not always getting full rate here. So, but because we're actually running the core here, why don't we use iPerf to just do the traffic, create traffic here and send it to the UE? And that's something that we can do with iPerf 3 actually. I just need to. Do you still see that? Yeah. Just starting the iPerf server here. One of the. So that's the console on this demo kit here, starting an iPerf 3 server.
Andre, will you do UDP or TCP traffic?
This is UDP now. So I'm kind of pushing actually more than the maximum, but using this iPerf 3 server. I have this application here. So it's
so remember that we recommend always to start with UDP because it gives you a better picture of the capabilities.
Yeah, exactly. I mean, that's just how we recommend to start with, and you can see here. I mean, we do have a little bit of Blair. It's not too bad actually. So yeah, so 782. Let's see, is the maximum, but you can see here 791. So according to the stats here, so not too shabby, I would say. Yeah, and this goes on here for a minute, so I can stop that here in the client. Yes. Or maybe let's also have a look at this. Remember when we did the speed test, we still saw some gaps. Let's do the same test again with the iPerf. So again, it's super downlink heavy traffic, so you'd still expect some gaps there because obviously there's also uplink slots. So one third of them are actually uplink, and those are the gaps that we see here. If this was a FTD cell, and we would be looking at the FTD frequency, you would see it all full, because the downlink is completely utilized, and the schedule would allocate all the resources to this one UE in the downlink on the downlink channel. But that's not the case here in this example, obviously. And that's also one example that Ismail showed there. You can see here the buffer, the downlink BS, or downlink buffer state. So that's actually the data that is coming to the so from the core to the max scheduler. So that's the buffer that the G node B has and the scheduler has in the RRC layer to allocate to the user. And maybe you run into a case where, although your RF conditions are excellent, so you have high CQI, maybe the case, or maybe you're doing downlink traffic, and despite having a high CQI, the MCS might not be very high. And one reason could be that the downlink buffer state is actually lower than lower than needed in order for the scheduler to allocate the highest MCS. So on average, it's enough to serve the buffer state, to serve the user, and that's why on average you see a lower MCS than 27 in that case, which is the maximum for 256 QAM. Yeah.
Why do you think the
Yeah, I can reply that.
Yeah.
So this is something actually really funny when you're not doing traffic, because first so if you are sending 2000 frames per second and one fails, the blur will be very slow. If you only send 1 per second and one fails, the blur will be 50%. So never look at the blur when the transmission is so low. And there can be also issues here with maybe the power, so the power boost that the receiver does not adapt the ATC fast enough. There could be many issues that can be happening. So typically the best is try to do full rate in uplink or downlink and then look at the blur there.
It also seems when other groups.
That's something that we can actually do. Let me walk out of the room. Okay. So I'm gonna stop the speed test here and just use the Ookla speed test and just use the downlink, like the iPerf. So right now CQI 15, right? Highest MCS. So I go away here. You guys tell me when it goes down. Good. Still too good. Oh, good. We come further away. Let me do a round. Huh? Yeah. Still there? That was too much. No. It's just the iPerf that stopped. No, we are still there. Yeah. Sorry. So not a lap. Still running. Yes. And then looking at this, so that's nice. No, you can clearly see the downlink rates going down and the MCS, down to 18. What is it? 19, 17. Yeah, this was the iPerf. Yeah, it just stopped. So it's a 60 seconds timer. Then we are back again. Cool. Yeah, I think, is there anything else we should maybe talk about, or guys are interested in any questions, obviously? Sure.
Just a general question. Do we have any training learning materials for undergraduate students, for new graduate students, for totally new to even cellular networks, internals?
Hello. So unfortunately, no. I can recommend a very good website for general wireless material, which is ShareTechNote. I don't know if you already know it, but actually we use it a lot to understand the specs. And I guess that the second, so in terms of our code, I would direct them to the application notes in our documentation or to the slides of this tutorial.
Thank you.
ShareTechNote. Yeah. It's a bit more complicated than that because you need to measure the power of the SSB block. So ideally, you would need test equipment like Rotenspars or Keysight that can demodulate the signal. And then this equipment tell you, they have a value and tell you SSB is X. And then, yes, you wire your RF, you put 30 dB or 60 dB attenuation, your measurement equipment, and then you can know which is the transmit power. But yeah, but this is, as I said before, ideally for a outdoor deployment or for a commercial grade deployment. In lab setup, you don't need that. Yeah,
Yes.
IQ scaling affects the power. Yeah. And actually, one more thing, in devices like this one, they have a configuration file in the firmware that allow you to specify the gain or the attenuation of every RF path. One extra step that you need to do is calibrate the full rate and calibrate the power of every path, because the paths are not exactly the same when we go out of the manufacturing, and you need to calibrate them. In MIMO, especially 4x4, it's very important that the powers of every port are balanced. Yeah. Yeah. Yeah, no, obviously. I mean, if you wire this directly to a test equipment, you need to put attenuation in between. So if you would need to check with the specs of your device and of the test equipment and of this. The maximum power of this, I don't know, don't remember, 23 dBm maybe.
But I think what he means is if he does not have access to the test equipment, if there is like a general guideline to do that. And I don't think that there is, I mean, it's working well enough to kind of, the same with the user P. I mean, it's, you kind of hand tune it, like try it out and see. There's no.
If you don't have test equipment, probably it's not a problem. It means that it's not a problem for you.
Yeah.
If you want to do a commercial grade deployment or in a campus, but you really want to look at long range, for instance, if you want to test long range communication or how far you can go or things like mobility, then you need to calibrate these kind of things.
So it's like you're flying that generally.
Yeah, mostly work. Exactly. Yeah. 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 Can you turn on the microphone?
Yeah. Can you tell us about the performance of srsUV with this setup, and what would be the future updates that we can expect from srsUV software?
Yeah, so as we said yesterday, srsUV is no longer in our roadmap. It's no longer a software that we maintain. We are hoping for the community to take over that. The performance that you can do, you can only do SISO. Right now, you can only do FDD. And I think that maybe you can do 50 megahertz, 40.
Yeah.
We
64 quant only, yeah.
So I asked this question because we are from like we are a PhD students, and we want to explore the UV side as well, because we want to modify the waveform, like those parameters, like scheduling parameters.
Yeah. Yes. In that case, if you want to experiment with the PHY, you need to use a configuration that is supported by srsUV. There is an app note in the documentation that describes an end-to-end setup with srsUV and explains the configuration that works. Yeah. More questions?
When setting up the system, we often find ourselves configuring the config files, changing parameters quite often to get the system to work in the state. Do you have any tools or techniques to simplify that process or make it easier when we're iterating through many different file changes?
You mean like a front end to generate config files?
Yeah, or do you do anything in your CI/CD that
No, no. In our CI/CD, so first of all, remember that there is also an option of passing a parameter as a value. So you can exploit this feature of concatenating multiple configuration files to have, for instance, the base config file that works for you, have some templates for when as he was saying, when the AMF is in the same machine, where it's in another, and then just switch between one or another. And then you can always override the parameter, the values that you have in the config file if you pass that value as a program argument. But I'm afraid the answer is no.
and that is a super great feature.
Yeah, I think with that we're gonna close the Q&A session, and I'm happy to hand over to Luis and for closing remarks.
Yeah, I'm looking forward to see all the research that you guys can do with this tool.
And hopefully we'll be around, so in case there's any questions.
Yeah, so I'll be brief. I'll take at most an hour and a half with my remarks now. Thank you so much for being here for these 2 days. Thank you to the SRS team for organizing all of this and for all the content that you put together. It's been great working with you all. You probably also brought the good weather from Spain, right? So 2 beautiful days. I think this kind of gathering is really important for the open source movement and for Open RAN and so on. So my hope is that we continue doing this. We have more opportunities to get together. I think this was really unique in terms of the mix of government and industry and academia. You don't see that much. You probably had the fewest no-shows of any conference that I've ever been in my life. So I think there's like 2 people who didn't show up, so which is really remarkable. But what makes everything work is also your participation, your questions, your discussions during the break. So I'm really happy that we had the opportunity to host this and hope that we can do it again next year and the years to come. So I'll let Paul have the last word.
Thanks, Luis. And absolutely, I think we're very keen to make something like this happen again. And I'd like to thank you very much for joining us. I think it's really made the event for us is to have so much active participation. And certainly, we'd love to hear your feedback on the event, on ways it can be improved. So get on Slack, write us an email. We'll probably send out a survey in the coming day or 2. So we're very keen to hear your thoughts on that. And finally, I'd like to really thank Luis and Aloysiu and the team here at CCI for hosting us and for helping us put this together, because it really wouldn't have been possible without them. And with that, I'll close the event. Thank you very much, everyone.